which is an assistant professor at the Hellenic Mediterranean University. His research focuses on printed photovoltaics and energy storage. He has a PhD in material science and technology and has received several prestigious fellowships, including the Marie Curie Fellowship. So today's Dr. Kakavelakis' presentation, entitled Solution Processed Carbon-Based Electrodes for Fully Printed Solar Cells, will cover the development of carbon paste and inks for creating fully printed flexible solar cells. He will discuss the benefits of using carbon electrodes in terms of performance metrics like power conversion, efficiency, and stability. So, Professor Kakavelakis, the floor is yours. And thank you once again for accepting our invitation to join this event.
Thank you very much, Irini, and for the kind introduction, and Kostas and Irini for the invitation, and in general, this initiative, the Infrachip program, and your the organization of the school for the invitation. I really much, I would say, enjoy also Professor Okipintis' presentation. I overlapped with him during my time in Cambridge, so I really appreciate his work and his really nice presentation. So let me share my screen, and yes, let me know if you can see my presentation in full screen mode. Is it full screen, or I need to swap the screens?
Not in full screen.
Is it fine now?
No, we cannot still see it in presentation mode.
Okay, let me. What about now? Not yet. So
no,
I will
at least
stop the
for
share,
me.
and I will share the entire screen in this case. So.
Okay.
Just a minute. Sometimes technology doesn't help very well. Done. Okay. What about now?
Now it's okay, I think.
Yes, now it's perfect.
Okay, so thank you very much. Now I will start my presentation. As Irini mentioned, the title of my presentation will be Solution Processed Carbon-Based Electrodes. I mean, its application can vary, on energy storage and energy generation devices. This presentation will mostly cover the energy generation sector, but all these kind of materials based on carbon base can be applied also for batteries, supercaps, etc. So it's a very dynamic topic. And the topic of today will be on fully printed solar cell, which is, I would say, higher TRL technology, but not commercialized yet. We will see pros and cons of this kind of technology. It's moving very fast, and it's very close to commercialization these days. Okay, so this is a short outline of my talk. I saw also yesterday's Professor Antonio Agresti presentation about photovoltaics and tandem devices. So my introduction about solar PV technologies, etc., will be quite short, thanks to Antonio, and then I will mostly discuss about the benefits of printed photovoltaics, carbon electrodes, and also a new concept of graphene electrodes and summary. So to introduce you on the topic, and especially to convince you on why solar, I mean, we have all seen the significant consequences of burning fossil fuels, from rising the CO2 levels beyond, the critical levels of 300, and also this gave rise to temperature increase, which is, every summer we see new records for temperatures around the globe. So this is, I mean, it's going to be very dramatic, and we have seen significant change of climate and ecosystem in our planet. So there is no, let's say, no more direct evidence that burning fossil fuels is a very, I mean, dangerous approach. And according to projections, if we continue to go towards this direction in 2100, I mean, in less than 75 years, in about 75 years, our planet's climate and ecosystem will be changed irreversibly and will have significant problems with our everyday life. So one, let's say, approach to tackle this problem is with the exploitation of solar energy. I mean, within 1 hour, our star, the sun, is providing the power, let's say, to power our global energy needs for 1 year. Of course, we need to develop the technology in order to exploit and utilize this kind of energy. And this is a very motivational map where we can see if we can cover, this is, of course, an imaginary, let's say, map. If we can cover these 6 dark spots in the global map, we can cover the entire global energy needs. Of course, we are not there yet for many reasons, and we will discuss this kind of topic in today's presentation. Considering today, we are only at 3% of the total global electricity production is covered through solar photovoltaics, and many different reasons are behind this very low number, including material development, technology development, and policies. Of course, in this presentation, we will mostly discuss about materials and technology. And in order to give, let's say, an introduction how a photovoltaic device works, this is a very nice explanatory diagram. So this is the band diagram, valence and conduction band of a typical semiconductor material used also in photovoltaic devices. And what we are observing here is when the photon of the sun, the energy source, is above the band gap of the material, an electron is getting promoted from the valence to the conduction band, and then connecting this material with electrodes and transporting materials that we will see later on. And of course, with an external circuit, we can either, in the case of photovoltaic device, exploit these kind of charges for electricity production because of the current generation with the current flow from the device. Vice versa, of course, it can work as an LED in case we, instead of extracting the charges, we, I mean, injected charges from a power source. Pretty much, this is very important for the students to understand the operating principles of a semiconductor device such as a solar cell. And key parameters in order to characterize a solar cell include the voltage output of the device, the maximum voltage output that is called open circuit voltage. So what is the voltage the device is generating at the open circuit condition? And this is always proportional to the band gap of the material. So as you can see, depending upon the band gap of the material we are using, always there is a voltage loss. We will discuss this, why this is happening. And this generating open circuit voltage lies below the band gap of the material. Vice versa is the photocurrent that the device generates at short circuit conditions, and this is always reversibly proportional to the band gap of the material. And very nicely, Shockley and Quasar predicted what is the maximum power conversion efficiency in a photovoltaic devices, and here it is depicted in this diagram that the maximum, depending upon the band gap, at 1.33 microvolts can go up to 33.3%. And here are the numbers summarizing the efficiency losses, including the thermalization loss because of the absorption of high energy photons, thermodynamic losses because of the quality of the material, radiative combination, and subgap photons that cannot be absorbed inside the semiconductor material of our photovoltaic device. So all this sum up to an efficiency loss of 66.7% at the optimum bandgap, and a maximum power conversion efficiency can be achieved of 33.3%. Now, going upon and continuing the presentation, we see this is a very famous map. If you want to do a benchmark of photovoltaic devices and photovoltaic technologies, you need to identify different materials used in the photovoltaic sector. Of course, the king material and that dominates around close to 95% of the total energy photovoltaic market is based on crystalline silicon with a technology that is very well, very well established in the market with efficiencies of around 26 to 27%. When it comes to alternative materials, we have the thin film technology and the emerging technology that we will mostly focus our presentation and our, let's say, introductory topic today, with materials such as dyes, organics, and hybrid materials such as lead halide perovskite. So we will discuss advantages and disadvantages. Of course, we need to first understand the potential of silicon. As I mentioned, the efficiency of silicon is pretty much coming close to the theoretical limit. With a bandgap of a silicon, the maximum efficiency that can be achieved using a single junction device is around 29%, and we are already at the edge of 27. So it means this technology is coming very close to the limit. And in order to further achieve higher efficiencies, we have to go either to alternative material with, let's say, more optimized bandgaps, or to use the approach that Professor Agresti mentioned yesterday in order to make the tandem configuration. So efficiency and stability for these devices is pretty, let's say, optimized. However, in order to create silicon, and I mean silicon as a wafer grade silicon or polycrystalline scale silicon at the PV, let's say, quality scale, this is a very complicated and very nasty industrial process that it is a multi-step process that takes into account let's say, high temperature and nasty chemical processing route. That from this kind of direction, we end up with a wafer scale crystalline, monocrystalline silicon that we have to, let's say, pass through all these processes that are very energy intensive in terms of electricity, let's say, consumption. So all in all, this is a very good technology when it comes to commercial landscape, but there is a very big penalty in material, how to achieve material quality. And later on, we will see with very simple processing routes, alternative materials solution process can be of very high quality, even with extremely low temperatures, close to room temperature processing. Another very interesting graph that shows, let's say, the potential of silicon. And let's say another big drawback is the development of the technology. Let's say the last few years, it is at the 100 gigawatt scale per year. And if we do, let's say, a very simple math of 100 gigawatt, this is, of course, the peak. So we need to divide this to an average by a factor of 5. We have an average, let's say, 20 gigawatts per electricity production a year. And in order to cover the 20 terawatt consumption for our global scale a year, we would need approximately, at this current, let's say, pace, we would need a significant amount of time in order to cover all this electricity consumption only from photovoltaics. Of course, as I mentioned in the beginning, it's not only about materials and technology, it is also about politics and, let's say, political decisions, but it would be extremely difficult to, let's say, process silicon materials with these so many, let's say, processing steps to achieve, let's say, high quality electronic scale silicon with all these kind of steps and processes that it takes to generate electronics grade silicon. Another important aspect, because when it comes to renewable energy technologies, we always think this is a very green technology. And unfortunately, for silicon photovoltaics especially, it is, let's say, the worst in terms of carbon footprint. Of course, don't get me wrong, during the operating lifetime of the photovoltaic device, this is, let's say, recovered, because during the operation of photovoltaics, there is no CO2 production. But when it comes to the production of the modules, the panels, etc., and as you have seen, of course, the silicon grade material, this technology is quite intensive in terms of carbon footprint. So in order to go towards this political directions of net zero, etc., of the European Union by 2050, we need to either lower this number or make our panels extremely more efficient, which is highly unlikely just for the single junction silicon photovoltaics. And all these third generation technologies came into the game because of our, let's say, inspiration. All this inspiration came from photosynthesis, because we have seen that, of course, it is possible to generate fuels and to do specific processes using sunlight and making the natural photosynthesis process using splitting water and creating, let's say, hydrocarbons and sugars in order to grow plants. So a similar process can be done through the exploitation of artificial photosynthesis. And of course, if we found a way to, let's say, exploit this kind of process and make it more efficient, because of course the natural photosynthesis process is of extremely low efficiency. If we can make it a bit better, we can harvest up to 95 terawatts by storing sunlight into chemical bonds. So this was a very big inspiration at the 1980s, and all this came into realization by the development of the so-called dye-sensitized solar cell, which mimics the natural photosynthesis with an artificial photosynthetic cell called dye-sensitized solar cell, where we have a typical dye that is sensitizing an electron transporting material, so a material that extracts electron from a typical molecular semiconductor such as a dye, and the dye then is getting regenerated through a liquid or solid electrolyte, depending upon the material we are selecting, and the whole system is regenerated through, let's say, a catalyst that is made mainly of platinum, a very expensive rare metal, deposited on a conductive substrate. Of course, this technology has been developed a lot, and nowadays we understand better. So this is a typical example of a dye-sensitized solar cell. And to explain you a bit more about how this type of device works, this is a very uncommon device, and it was very surprisingly that if we use a single crystalline titanium dioxide material, the device has a very poor optoelectronic response. And this is mainly because of the surface area of the titanium dioxide particles. So if we use a mesoscopic scale titanium dioxide film, we can increase the surface area of the dye, let's say, absorption at the surface of the titanium dioxide. And in this case, we have seen external quantum efficiency. So what does it mean, external quantum efficiency? How many photons are created are generated, are contributing to the current generation of our photovoltaic device. And this was a very, let's say, motivational work, because this was the first time that we have seen a photovoltaic device works beyond the p-n junction, what I mentioned in the beginning of my presentation approach. This is the first three-dimensional junction that works with a very high efficiency. external quantum efficiency of approximately 90% at the peak, and power conversion efficiencies of, around 15% upon solar irradiation. And a very big development for this kind of technology came through the development of solid-state electrolytes. This is a very important topic also for developing batteries these days. Why so? We will see later on. Instead of having, as I show you in this picture, in this schematic, a liquid electrolyte for the dye regeneration, scientists were able to replace the liquid electrolyte with a solid-state electrolyte, which was very important for the development of solid-state photovoltaic devices. Why? Because if you have a liquid electrolyte in your device, it's highly possible that this liquid at some point will become solid and the device will have a sand pathway and it will stop working because of all these electrolytes were based on low temperature solvents at that time. And this was a very big development, these solid-state devices, for the development of a new kind of technology that will be the main topic of our discussion today. And I hope the students will extend their knowledge in this type of materials, the so-called perovskite materials, hybrid perovskite materials. In this case, the first development was through the incorporation of nanocrystals based of lead halide perovskites, methylammonium lead iodide and methylammonium lead bromide. Antonio gave a very nice introduction about the materials yesterday, so I don't need to spend too much time upon this. But the main idea here was to replace the liquid molecular sensitizers with solid-state perovskite nanocrystal sensitizers. Of course, the efficiency of this type of device was not very high, approximately 3.9%. If you are more interested to know details about this, you can follow this reference. And the reason was especially because in this type of device, the scientists used liquid electrolytes. So what happened? The material, the perovskite, was very prone to dissolution from the liquid electrolyte. And in the rest of my presentation, I will show you how the field progressed from 3.9% to more than 26%, 26.7% these days. And of course, to explain you the problems towards commercialization, because one will ask me, okay, the efficiency is 26%, why don't you commercialize? I will explain you, at least I will try, why this kind of technology is not yet at the market. There are practical and material science reasons behind this. So Antonio gave a nice introduction just to inform if someone was not present at the Antonio's presentation, or at least to, let's say, refresh our minds. These materials are based on a crystalline structure of ABX3 formulation, where the A is a typical either organic, such as methylammonium or pharmamidinium cation that can fit in this cubic structure, and the B is a typical metal, so it's a hybrid or fully inorganic, depending upon the cation. The B anion is, the B cation is either tin or lead. Recently, we have seen also bismuth and silver combination for double perovskites, but let's stick to the typical material. And the X-site is mostly for the highly efficient device iodide, and with some traces of bromide and chloride for controlling crystallization of the material. So this kind of material, they have a bandgap of up to from 1.2 up to 3 electron volt, depending upon the composition of the material. And of course, for the highly efficient devices, utilizing bandgaps very close to the optimum, with a composition of formamidinium lead iodide perovskite thin films. And the very big discovery happened around 2012, so already 12 years ago, with the four different groups developing solid-state devices. So up to then, all the devices based on the sensitization either of molecular or perovskite materials was based on liquid electrolyte devices with the highest efficiency of around 10% at that time. And overnight, with the development of the solid-state devices based on lead halide perovskites, either nanocrystals at the very beginning. So what you see here is a titanium dioxide covered with an extremely thin absorber of nanocrystals of titanium dioxide, or having additionally a capping layer of lead halide perovskites. Overnight, we have seen efficiencies of more than 11 to 12%. So this was a very good sign that this kind of material is of very high electronic quality. And from 2009 that we have seen the first publication, we have surpassed the 1,000 publications a year on year 2019, and now we keep growing upon this number. And we have seen how important was the development of a solid-state perovskite sensitized solar cell, because let's say the first publication was a bit underlooked in the beginning, and as soon as these 4 papers published in 2012, then we started seeing this exponential growth. A bit of a reminder from your yesterday, let's say, class, why these materials are so special, because they combine both the organic and the inorganic worlds, let's say the benefits of both of them. So what is this about? Solution processing. This is the topic of the presentation. So we can create solution process semiconductors at extremely low temperatures, even at room temperatures these days, or close to room temperatures, with the benefit of the extremely high absorption coefficient. So if you do the mathematics, if you have a typical material thickness of around 700 nanometers, you can absorb 100% of the incoming light. And of course, this is due to the direct band gap absorption profile or nature of this kind of materials. Other important things, if you want to make tandems or facade applications, you can tune the band gap very easily. We have seen this through compositional engineering. And why this is so efficient? Because, of course, they have extremely high diffusion lengths of electrons and holes. These days, we have seen up to 10 micrometers. So imagine if you have, let's say, a thickness of 1 micrometer that is enough to absorb 100% of the incoming light, you can easily, let's say, put your electron and holes inside the thin film, and it will travel without any problem throughout the material before recombining. This is extremely important. And of course, this is the final outcome. This gives rise to extremely low losses at the let's say VOC, which is a very big indication about the electronic quality of the material. And we have seen the typical polymer organic semiconductors. They have very, let's say, high energetic losses, low VOCs, or vice versa. The perovskite materials, they have very low energetic losses depending upon the band gap of the material. I mentioned about the solution processability, the ease of processing the materials. Just to give you an example, you can easily mix a bunch of precursors. Here we see 2. Sometimes we would need a little bit more, some additives in order to stabilize the material, and typical organic solvents in order to make a solution, and then use typical techniques in order to deposit the material. Of course, this easy processability comes with a penalty. As easily the material is formed, the same is with the deformation. So if we heat the material at a certain temperature, or we expose the material at a certain temperature or humidity or biasing condition, the material may fail from a, let's say, perovskite grade to lead halide grade. So this is one of the things that, let's say, slow down a bit the commercialization of this kind of technologies. And thanks to the processability of this kind of material, we can use different techniques, such as blade coating, slot die coating, even inkjet printing and spray coating, in order to make large area films, which is part of this infrachip, program, in order to make large area printable electronics. So the typical method in order to make large area perovskite materials, and especially perovskite thin films, is by using the blade coating approach, while in order to make the transporting materials, you can easily make them through spray coating or doctor blading techniques. Now, let's move from the material to the device level. We have seen different kind of, let's say, configurations. We started from the extremely thin absorber, so utilizing the DSC, the dye-sensitized solar cell configuration, where typically so-called the second generation dye-sensitized solar cell, or the first generation perovskite solar cell, when with the addition of the capping layer of the perovskite, we have gone to the mesoscopic device, and then it is possible also to go in a completely planar configuration, so PIN or NIP, depending upon the position of the hole and electron transporting layers. We can even have a completely planar device configuration. Now, regarding the operating principle and let's say material placement as a sandwich configuration, of course, we need a transparent conductive electrode. In the most of the cases, we would need an indium tin oxide or fluorine doped tin oxide. We will need on top of it to deposit a very high let's say electron extraction property material, a very good electron extraction material, such as titanium dioxide, or even carbon alternatives, such as fullerene derivatives. And then we will deposit our perovskite semiconducting film, a whole transporting material, such as the solid state spirometad, and then we need a metallic contact in order to select and collect the current that is generated throughout this device. And then now that we have the solid understanding of the device configuration, of course, we need to shine light from the transparent conductive oxide side, and this incoming light has to reach the metal halide perovskite material in order to promote, to provide the energy to the electrons that are inside the valence band of the material, and to promote them in the conduction band, that this will enable the, let's say, transport of the electrons that will give rise to the current flow and the electricity production from this kind of device. Thanks to the extremely good properties of metal halide perovskites, such as high diffusion lengths, all these electrons can travel easily within the material and separated at the interfaces with the electron and hole transporting layers. So unfortunately, there is a bunch of P and N type contacts, such as I mentioned mainly titanium dioxide, but there are many materials for electron and hole transporting layers, and different, let's say, alternatives for the perovskites, thin films. We have seen only a few metal contacts, such as gold, silver, aluminum, in order to make the metal contact. And all these highly efficient devices are, for the moment, based on this typical configuration, where we have a metal contact in order to collect the electrons and the holes for the current generation. And all these kind of devices easily surpass 25 to 26% with this kind of typical device configuration. I will not go through all the different, let's say, examples. Here is, for example, an example on how to modify, let's say, the bulk of the perovskite in order to make the material, let's say, of higher electronic grade. Here we see a lower ideality factor, which is important for this kind of device. Here we see the importance of adding and modifying the electron transport layer of this kind of device with mesoscopic TiO2, quantum dot tin oxide, etc., with devices approaching 26%. Also, highly stable devices because of 2D, 3D, let's say, engineering and the interface between the perovskite material and the transporting layers, extremely stable devices. And also, here is another example of sensitizers in order to do a similar approach for the interface and engineering to make devices efficient and stable. But all these things come with an expense. So especially regarding materials and devices based on the NIP device configuration, we have seen extremely high efficiencies, up to 26.7%. But the main obstacle towards commercialization is, of course, one is stability and the second is upscaling. And when it comes to typical NIP device configuration, when we need gold in order to make our counter electrode, this is coming with an extremely high cost. So we have done in my previous group some estimations of gold expense will be twice as much as the typical silicon solar panel, only considering the cost of gold. Okay, so this is extremely high cost to use gold, and as well as we will need expensive equipment that are not also very upscalable. So we are not tackling, if we are going towards this direction, irrespective of a metal, if it is aluminum, silver, or gold, if we are using this kind of tools, we will have extremely low throughput because we need to load and unload our devices in a thermal evaporator. The very big problem besides the cost is the stability that we'll need to understand. There is a prone of, let's say, oxidation or degradation at the interface with the typical cold transporting materials such as pyrometal. So either we would need to have an extra material such as chromium, or in order to solve this problem combined with the cost, we will need to get rid of gold or silver or aluminum, in general. So we will need to find an alternative, and this alternative was first, demonstrated from Professor Grätzel in 1996, first, of course, in dye-sensitized solar cell, where he demonstrated the use of carbon, and I will explain you in a minute what carbon means in general. So he introduced a carbon paste in the pilot line of this dye-sensitized solar cell, and instead of using platinum as the catalyst, he used a carbon paste to catalyze the process of the dye regeneration. So when upon, let's say, discussing upon the development of perovskite solar cell, there is a huge intense field of replacing metal electrodes with carbon electrodes. There are two main device configurations, the so-called triple mesoscopic, where the carbon is deposited as a porous layer, and the perovskite is infiltrated throughout the device, so it touches even the porous scaffold of titanium dioxide, which is giving rise to a lot of recombination at this interface. And of course, in order to mimic the typical device configuration of this NIP device configuration, just by replacing the gold with a thin film of carbon electrode. Thin film, I will explain to you how thin. And when it comes to carbon, now I will introduce you to this fascinating topic. We mostly discuss about graphite and carbon black. Why graphite? Because it is, let's say, the conductive filler inside the paste, and carbon black in order to fill their gaps between the large chunks of the graphite flakes. And of course, we will need some solvents and binders to formulate our conductive paste. And well, now when it comes to incorporation of this paste inside the device, it's a multi-engineering task because we need to understand and optimize different aspects of the carbon paste, such as, of course, conductivity, because metals are very highly conductive, but also chemical compatibility. So if we discuss about this particular device configuration, it is extremely important to have the chemical compatibility, solvent compatibility, and of course, the processability of the material, not to destroy the layers that are built below. The first development of a fully printed carbon-based device was with the triple mesoscopic device configuration, where this Chinese group from Wuhan, they made the first demonstration of the carbon-based perovskite solar cell. The efficiency was very low, especially because of this, what we mentioned, the perovskite was infiltrated and was with a direct contact with the TiO2 layer. So there was let's say the carbon and the TiO2 was giving rise to extremely high recombination at the interface. So through the development of this technology, we have seen let's say, engineering both at the interfaces and bulk material level. And also the very important things about this kind of technology is that it can be, for example, fully printed, of course, besides the FTO. Even the silver that lies at the edge can be using a silver paste in order to serve as a current collector at the front and the back contact, fully printed all the layers, and also we can use different techniques such as inkjet printing to infiltrate the perovskite composition and make really large area devices, such as even up to today, even 900 square centimeter devices that can go at this kind of scale for a single module. Some very important, let's say, development for this kind of technology was the development of engineered materials in order to have some specific A-cation, let's say, configuration in order to somehow block the direct contact of carbon and TiO2 that in this case, the recombination at the interface was significantly suppressed and efficiencies of up to 12% even in a module size was achieved. And additionally, other approaches in order to improve the efficiency or the stability of this kind of cell is to let's say, adopt the engineering that was developed for the typical metal-based devices, such as the gold. And what kind of approach do I mean in this case is the 2D, 3D engineering. So to, let's say, passivate the top surface of the perovskite material and integrate this approach with within the carbon-based device configuration with modules of more than 10% power conversion efficiency and 12,000 hours, which translates to one full year of complete device operation with this kind of approach. Similar approach was utilized to make the first ever perovskite solar panel based on carbon electrodes. This was done in 2017 in Wuhan, in China. And this is now, I don't remember the name, but there is already a company in Wuhan who is driving the commercialization. So they have already, this is a 9 square centimeter string of perovskite solar panels built upon this kind of technology. But as you see, the efficiency of this kind of devices is not even close to the silicon or high efficiency perovskite solar cell. So there is a continuous development upon this device configuration. Additionally, we have seen other works, and of course, the importance of the carbon ink that I mentioned a few slides before. It is extremely important to use specific solvents. So this here is a very good example if you want to go through it and if you are interested in the topic, you need to find a specific formulation of your solvent, of your carbon paste, and of course the binders that are not deteriorating the quality of the perovskite material or the whole transporting material. Of course, there is always a trick of engineering when you can place an interfacial layer between the perovskite, such as the 2D, 3D engineering, or the interlayer between the HTM and the carbon in order, let's say, to slow down this degradation process. But it is extremely important to have a look on the boiling point of the solvent, and also the compatibility test that needs to be done upon the chemical and solvent compatibility of the paste and the materials that are lying beneath. So if you're properly engineering the material and the device configuration, very stable devices with above 15% can be achieved. Of course, it is also possible to play with alternative cold transporting materials such as copper thiocyanate or other, let's say, more stable materials compared to spirometal. This is an example published from EPFL a few years ago. They show what the engineering of the perovskite material and the perovskite material cold transporting material interface, and they demonstrated a very high efficiency, especially at that time, of more than 18% for a carbon-based device with very high stability even upon continuous thermal stress or UV exposure, etc., of more than 1,000 hours, which is very promising considering the high efficiency of this type of devices. Another very interesting approach is to use...
George,
yes?
Apologies for interrupting you. Just to remind you, we have only 10 minutes, 12 minutes left.
I will be done in 2 minutes.
Summarize in 1-2 minutes, then applicants can ask questions. Thank you.
Thanks for the kind reminder. So another interesting approach is you can, instead of using a whole transporting material, you can find a passivator layer that forms a very strong interface between the perovskite and the carbon interface, and this can even give rise to a very high whole extraction rate. This was demonstrated from this group, and efficiencies of more than 19% were demonstrated. And of course, the main explanation behind this high efficiency is that this passivator material or the 2D perovskite blocking layer was blocking the recombination at the interface. And the very surprising and interesting approach is that they have done also a simulation that if you use this kind of approach, fill factors of exceeding 86% can be achieved, which is very close to the typical highly efficient 26.7% devices. So in order to summarize my presentation, it is extremely important to tune the properties of the carbon paste in order to make the let's say the ink, the carbon ink compatible with the perovskite or the transporting layers, but it's also important to engineer the material, the carbon paste. So in order to somehow control the air gaps between the the graphite flakes and the carbon black. There is the key parameter in order to reduce recombination and also, of course, reduce the heat resistance or the conductivity of the material, because as you have seen, with a typical type of carbon paste, the heat resistances that can be achieved are above 10 ohm per square, which is not beneficial especially for large area devices, but even for solar cells at an even small scale. Graphene can play an important role, and I will summarize here. It is possible to engineer the flakes of carbon using different methods. One example is this one, the so-called high pressure homogenization. You can also use typical approaches such as exfoliation in a solution, such as sonication, electrochemical delamination, etc., where you can process the graphite flakes in order to tune their properties, such as especially the flake size and thickness, in order to control the interface and make films with a specific dimension and let's say distribution that is very important for the, let's say, reproducibility of the material, but also it is also important because it gives rise to very compact films that are able to make extremely low heat resistance or highly conductive materials. And we have seen that it gives rise to, let's say, very high reproducibility and very, let's say, huge stability of the carbon ink itself, and efficiencies of above 15% in a module scale, and also highly stable devices with extrapolated lifetimes of approaching 8,000 hours, which is a very promising result for industrialization. And when it comes to cost now, why it is important to achieve 15% efficiency on a, let's say, module scale, because combined with the 15 years lifetime, which can achieve a levelized cost of electricity, so in simple words, dollars per kilowatt hour of less than $4 per kilowatt hour, which is well below the typical energy generating technologies, including fossil fuels. And this is very promising and will give rise to a photovoltaic technology that at the end of the day will be, the cost will be driven from the TCO, so the transparent conductive oxide, and the processing of it for the module preparation. So this was my presentation. So if you want to keep a message from this topic, carbon is a very highly promising material in order to replace metal electrodes in specific photovoltaics, such as dye-sensitized solar cell and perovskite solar cell. But we have to give specific, let's say, attention on how to formulate the material with a specific graphite, with a specific binders, solvents, and of course combined with the interfacial engineering of the device in order to achieve minimum interfacial recombination and thus high, let's say, photoluminescence and electroluminescence quantum yield that will produce highly efficient devices. So processing carbon is extremely important in order to do so. So before I finalize my presentation, I want once again to thank Kostas and Irini for the invitation, Infrachip project for this excellent initiative, and also our students for eminent for attending and giving attention to this important school that will give very important information about printed electronics on energy generation and storage devices. This is my email. If you want to contact me, please do so using this email. Thank you very much, and I'm looking forward to your questions. Thank you.
Thank you very much, George. Very nice presentation, detailed one. So I think we have 5-6 minutes for a few questions. Maybe Irini, I think that one of the questions in the chat.
Yes, George, again, thank you. First of all, for accepting our invitation to give this talk and for the really, really interesting presentation. So I will start with the first question. Is there any other kind of perovskite material lead-free which has also such low band gap? Does this methylammonium lead iodide perovskite material has piezoelectricity and ferroelectricity like other perovskites?
Thank you very much for the question. Indeed, it is possible to tune the band gap because, as I mentioned, the formamidinium lead iodide, which is the main driving force of the technology nowadays, is around 1.5 electron volt material. So it's a bit far away from the optimum band gap. So it is indeed possible to go even below. So one way is, of course, to substitute a lead metal with a tin metal. Of course, this is coming with extreme cost with the stability of the material, because tin is prone to +4 oxidation. But there are ways in order to overcome this, especially with antioxidants. If you want to go through very specific publications that were published 1-2 years ago, you can look about antioxidants for lead-free perovskite. It is a very fascinating field in the lead-free perovskite, but unfortunately, the electronic quality of this type of materials is significantly inferior compared to the lead-based materials. So the maximum efficiencies achieved so far are about 15 to 16%. So yes, it is important to develop these materials if you want to follow Professor Agresti's topic, because this is a very interesting, an incoming research direction, the tandems, and it is possible to make highly efficient tandem devices utilizing especially these tin perovskite materials to stack them with the wide bandgap perovskite based on lead. Now, the second part of the question was about the piezoelectricity. Unfortunately, I'm not the right person to ask this question. I'm not very well aware of the piezoelectric. I'm not dealing a bit on the piezoelectric properties of the lead-based perovskite materials. I know this, the oxide perovskite materials are very good for piezoelectricity. If you want to send me an email, I can have a look, and I can reply to your question later on if it is okay with you.
Okay, thank you. And we have another question. How can the work function of carbon-based electrode be fine-tuned to better align with active layer in different solar cell architecture?
Okay, thank you very much. This is actually very important topic that is a bit overlooked. One possible way, now I guess we are discussing on these solution processed materials such as graphite and graphene, etc., or this, let's say, derivatives of this type of materials. It is indeed possible, and there are some, let's say, works in the literature. And one possible way, for example, is to utilize the doping process. So, for example, to, let's say, modify the periphery group of this kind of material, such as graphite, for example. So the graphite flakes can be tuned by doping on functionalization with a specific chemical routes, of course, or by substituting, let's say, other metals in the carbon plane. I remember now there was a paper from the Wuhan group where they doped these carbon electrodes with nickel atoms, and indeed this gave rise to a higher work function, because the typical work function of this type of materials is from 4.9 to 5.1, and these perovskite materials typically they have a very deep work function around 5, especially the valence band in the work function of around 5.4 electron volts, especially for mamidinium lead iodide. So this is a very good question, because it's let's say an open topic on how to finely tune the graphite flakes, but at the same time it gives rise to defects. We have seen myself, I have seen with the Raman characterization on when we are trying to modify the graphite flakes with some external stimuli, such as functionalization or fragmentation, etc. We have seen the rise of the D band in the Raman spectra, which is a very important indication of defects, and then you start losing, let's say, the important properties of such as conductivity and solution processability because of the very high defect density of the material. So it is possible, yes, but you need to be extremely careful, otherwise you will deteriorate the electronic properties of your carbon electrode.
Thank you so much. Another question is, what is the difference between
Maybe the final
pseudo
question,
fill factor and
the final
Yes.
question, because we are
one
already
final
over.
question? What is the difference between pseudo fill factor and fill factor?
Okay, thank you very much for the question. Pseudo fill factor means in this work, what these people they have done, let's say, an electrical simulation, having a perfect interface. What does it mean, perfect interface? They have simulated their device. What will be, let's say, the electrical output if there is no, let's say, non-radiative recombination at the bulk, or in general, recombination at the interfaces between the photoactive material and the electrode interface. So what they have done, they have created, of course, in a simulation study, a perfect interface and a perfect bulk, where the carbon electrode, let's say, is a completely compact, and it doesn't have any air gaps between the electrode and the interface with the perovskite. So what they have done, they have calculated what is the maximum achievable fill factor it can be possible to be achieved within this kind of device. So it is 86%. This is very promising because of course, in this specific work, instead of having a very thick whole transporting material such as pyro, which is 200 nanometer, they utilized an extremely thin, as far as I remember, octylammonium lead iodide passivator surface of few nanometer, and they have seen that it is possible to extract photoexcited holes from this interface, which gives rise to very high fill factor, because the carbon electrode and the perovskite interface is very, very close to each other in order to avoid recombination within the whole transporting material. So it is a very promising direction, need to be explored on how to fill all these air gaps that are formed in your experiment, of course, when you form a carbon electrode on this kind of material such as perovskite or whole transporting layers. I hope that I addressed your questions. And if there is any additional one, I can go through offline and address it.
Yes, I think we can send you, compile the questions, send you an email, and then we can forward your reply to the applicants or the school. So with this, I would like to close the second day of the school right now. We are already 5 minutes after the official termination. So thank you again, Professor Kakavelakis, for this great presentation, and also all the applicants for your attendance today. And of course, Irini, always.
And see you tomorrow.
Coordinating everything. So see you tomorrow.
Bye-bye.
Bye.